Here's the million-dollar question. Would the moon still exist if no one's looking at it? This sounds ridiculous until you examine how particles behave in the quantum realm. Today, we'll explore the experiment Einstein called spooky and what it reveals about the fundamental role you play in creating reality. Have you ever wondered what light really is? For centuries, scientists debated whether it's made of tiny particles, like little grains of sand, or whether it's something more fluid, a wave, like ripples in water. Then, in 1801, a physicist named Thomas Young conducted a simple experiment that changed everything. He set up a light source to shine through a barrier with two slits cut into it, and on the other side of the barrier, a screen to observe what happened. At first, this setup seemed innocent enough, like a classroom science demonstration. But what it revealed would upend everything we thought we understood about reality. Here's how it works. When light passes through the two slits, you'd expect it to behave like bullets being fired through two holes, producing two bright lines on the detector screen. Simple. But when Young ran this experiment, that wasn't what happened. Instead, light created a strange pattern of alternating bright and dark stripes across the screen. A classic wave interference pattern. It was as if the light, instead of traveling in straight paths, spread out like a wave, interacting with itself along the way. This alone was surprising, but it fit with the idea that maybe light moves like a wave, with crests and troughs interfering to form that pattern. Einstein himself called light packets of energy, but this experiment showed something much more puzzling at play. Now, here's where things get eerie. In later versions of the experiment, scientists added a way to check which slit the light passed through. With this capability, they could measure whether the light was behaving as a particle or wave. But when they did this, when they tried to observe which slit the light went through, the whole interference pattern disappeared. Instead, the light started producing two neat lines on the screen, as if it were behaving like particles after all. It's like the light somehow knew it was being watched and decided to act differently just to mess with everyone. Imagine it like this. Picture you're tossing two pebbles into a calm pond. The ripples created by the pebbles meet and overlap, forming patterns across the water's surface. This is wave interference. Now, imagine that the moment someone looks at the pond, those ripples freeze into discrete little points, solid particles, mid-air. That's exactly the kind of paradox the double-slit experiment exposes. The way the light behaves depends entirely on whether someone or something is observing it. Without observation, it exists as an overlapping wave-like probability. With observation, it collapses. This is the heart of what scientists call wave-particle duality, the idea that light, and indeed all matter, exists in a limbo state of both particles and waves, flipping between the two depending on circumstances. What's baffling is that this observation rule doesn't just apply to light. Later experiments using electrons, which are some of the fundamental building blocks of matter, showed the same kind of behavior. Even when fired one at a time through the slits, electrons still created an interference pattern until someone checked to see which slit each electron went through. Now, if this sounds unsettling, you're not alone. When early quantum physicists began to confront this strange interplay between measurement and reality, many were deeply disturbed. Albert Einstein, famously skeptical about quantum physics, hated the implications of this experiment. He described the results as spooky, not just because they defied classical laws of physics, but because they seemed to suggest some deeper, almost ghostly connection between the act of observing and the existence of reality itself. Richard Feynman, one of the most brilliant physicists of the 20th century, had his own thoughts about the double-slit experiment. He once said it contains the only mystery of quantum mechanics. In other words, if you can wrap your head around what this experiment reveals about the universe, you'll have grasped the essence of quantum theory, though he also admitted it's nearly impossible to explain in classical terms. Because how do you even begin to rationalize something so counterintuitive? The challenge here is that classical physics assumes the world has objective properties independent of whether anyone is observing them. But the double-slit experiment tells a very different story. It suggests that observation isn't just a passive act, it has the power to shape reality. Without someone, or something, actively observing, light doesn't settle into a single state. It exists as probabilities, spreading out as a wave. Observation forces it to choose, collapsing it into a specific form, wave or particle. And this raises a question no one yet has a satisfying answer to. Why? Why would observation, something intangible, like simply gathering information, have such a profound impact on the physical behavior of particles? Could it be that the universe is somehow incomplete until it's being watched? Or is there something even deeper happening, something beyond our current understanding of physics itself? One thing's for sure, the double-slit experiment doesn't just explain light, it exposes cracks in the foundation of how we think reality works. What we perceive as solid, predictable, and independent might actually be tied to us in ways we never imagined. Some physicists and philosophers even wonder if this points to consciousness as a key player in the universe. But before we plunge into that philosophical abyss, let's first take this strange experiment one step further. What happens when we replace light with something larger, like electrons, particles that make up the very fabric of matter? Prepare yourself. The results are as bizarre as they are unsettling. Imagine this: you're firing one electron, just one, at a time through the same double-slit setup we talked about earlier. What would you expect to see? Most people might assume it would hit the screen and leave a single dot behind, like tossing a pebble through a small hole and watching it land on the ground. It seems logical, right? After all, an electron is a particle, one of the tiniest building blocks of matter. But if this experiment has taught us anything, it's this: logic takes a back seat when you're dealing with the quantum world. Here's where things get strange. When electrons are fired individually, something truly unexpected happens. Over time, if you let enough electrons pass through the slits, you don't just see a chaotic collection of dots on the detector screen. Instead, you get an interference pattern, the exact same pattern you'd see if you were shining waves of light through the slits. It's as though each electron isn't traveling along a single path. Instead, it's behaving like a wave that spreads out and passes through both slits simultaneously, interfering with itself. Think about that for a moment. A tiny particle, one that makes up the solid objects around you, seems to exist as a wave when no one's watching. This behavior suggests something profound. Before we observe it, the electron exists in a state called quantum superposition. This means it doesn't have a definite path, position, or even a defined identity as a particle or a wave. Instead, it's a combination of all possibilities, taking every possible route at the same time. It's a bit like flipping a coin, only in this case, the coin doesn't land on heads or tails. It lands on heads and tails at the same time, simultaneously embodying both outcomes until someone looks at it. Then, and only then, does it choose one. This idea of superposition is one of the cornerstones of quantum mechanics, and it fundamentally challenges how we think about reality at its most basic level. In the classical world of everyday experience, objects are where they are, moving how they're moving, completely independent of whether you're paying attention to them. A car doesn't exist as both parked and in motion. Its state is definite, no matter who's looking. But at the quantum level, particles like electrons don't obey those rules. An electron's state only becomes definite when it's observed or measured. Until then, it lives in a cloud of possibilities, embodying potential rather than certainty. This defiance of logic raises uncomfortable questions. If particles of matter don't have fixed states before they're observed, does that mean the physical world is fundamentally undefined until someone looks at it? And if that's true, does reality even exist independently of observation? Are we, at some level, not just observers of the universe, but co-creators of how it unfolds? This defiance of logic raises uncomfortable questions. If particles of matter don't have fixed states before they're observed, does that mean the physical world is fundamentally undefined until someone looks at it? And if that's true, does reality even exist independently of observation? Are we, at some level, not just observers of the universe, but co-creators of how it unfolds? To put this into perspective, let's try a more grounded analogy. Imagine you're walking through a hallway with two doors leading to the same room. You're invisible, so no one's watching where you go. Instead of choosing one door or the other, you somehow take both doors at the same time. Once you're in the room, your presence is seen as a mix of both paths, overlapping. But as soon as someone places a camera at the doors to figure out which one you're entering, you suddenly pick just one. Your ability to take both routes disappears the moment someone tries to observe what's happening. This isn't how things behave in the everyday world. But for electrons and all particles, it's just how reality works, not simply see. Even more unsettling is the fact that this quantum behavior isn't limited to electrons. Protons, neutrons, and even larger molecules have shown similar results in experiments. Scientists have even managed to demonstrate wave-particle duality with objects as large as whole molecules. The implications are staggering. If tiny particles and even clusters of atoms can behave this way, who's to say that larger systems don't have similar, hidden quantum behaviors we simply haven't detected? The single electron experiment forces us to leave behind the comfortable, deterministic rules of classical physics. Here, there's no preordained path, no strict cause and effect. The physical world, as described by quantum mechanics, is probabilistic. Each particle's behavior is a result of probabilities rather than certainties, and observation plays a decisive role in its ultimate state. It's a shift that even today feels counterintuitive, but it's one backed by an overwhelming body of experimental evidence. Now, this opens another Pandora's box of sorts. If observation collapses the wave function, fixing the state of a particle in the present moment, could this same act of observation influence something that has already happened? Could we make decisions in the present that appear to retroactively alter the past? As strange as this sounds, some quantum experiments suggest that the answer might be yes. Imagine this. A particle is on its way to a pair of slits, moving along its mysterious quantum path. It either behaves like a wave, passing through both slits at once, or as a particle, choosing one specific slit to travel through. Now, you might assume that by the time the particle reaches the detector screen and creates a pattern, its behavior has already been decided. Its journey is finished, and you're simply viewing the end result. But here's the twist. In the delayed choice experiment, scientists decided to make the observation whether to look at which slit the particle traveled through or let it create a wave-like interference pattern after the particle should have passed the slits. And somehow, that decision changes what happens. It's not just strange, it feels downright impossible. In our everyday world, the past is fixed. It doesn't change based on decisions we make in the present. Once something happens, it's done. But quantum mechanics throws that certainty out the window. In the delayed choice setup, the particles act as though they wait for us to decide how to observe them. If scientists choose to measure which slit the particle passed through, the interference pattern disappears, and the particle behaves like a particle. But if they decide not to measure, the particle behaves like a wave, creating the interference pattern as if it traveled through both slits. The truly baffling part? This decision to observe happens after the particle should have already passed through the slits. It's as if the act of observation reaches backward in time and rewrites what the particle did. Let's step back for a moment. You might be wondering how this even works. Imagine the experimental setup again. A pair of slits, a detector screen at the end, and particles, maybe photons or electrons, fired one at a time. Normally, without any interference, they'd produce the wave-like interference pattern on the screen. Now, scientists add a device that can determine which slit the particle passes through. But here's where they introduce the delayed choice. Instead of deciding right away whether to measure the particle's path, they wait until after the particle has passed through the slits. This should be too late to change anything, right? But the particles seem to suggest otherwise. It's like they retroactively decide what they were doing based on the choice made in the future. To make sense of how surreal this is, let's use an analogy. Imagine you're streaming a movie and you only decide halfway in whether to watch it in black and white or color. As absurd as it sounds, your choice changes not just the rest of the movie, but also how the first half was presented. color or black and white, from the moment you started watching. The very idea feels like something out of a science fiction novel. Yet, experiments like the delayed choice experiment are real and have been conducted with consistent results. What this suggests is profound. The future might have the ability to influence the past, or at the very least, our understanding of cause and effect doesn't work the way we think. This blurring of time and causality has led physicists and philosophers alike to ask some difficult questions. If the universe seems to wait for us to observe before locking in a past event, how can we ever think of the past as truly fixed? Is the world dynamic, constantly shifting based on choices and observations being made, not just now, but in the future as well? And if observation plays such a critical role, is it even meaningful to think of reality as existing independently, outside this process? The delayed choice experiment also hints at an even deeper mystery: the interconnectedness of particles across space and time. This is reminiscent of quantum entanglement, a phenomenon where particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. Some physicists speculate that this interconnectedness could explain the strange backward-in-time behavior in the delayed choice experiment. It's as if the particle and the observer are part of the same symphony, their roles interwoven in a way that defies classical logic. What's equally fascinating is that these findings force us to reconsider how time itself works. In classical physics, time is a one-way street. It moves forward, from past to future, and its flow is independent of everything else. But quantum mechanics seems to suggest that time is more flexible than we imagined. Events don't just flow in one direction. Instead, there's a kind of quantum feedback loop, where what happens now influences what already happened. It's unsettling, isn't it, to think that the comfortable arrow of time might be an oversimplification of something far stranger. So, what does this mean for how we understand reality? If observation not only influences the present, but also retroactively determines the past, what role does the observer truly play? Is it possible that reality itself doesn't exist until it's been observed? Could the universe be more like a canvas waiting for a painter's hand, incomplete until someone decides to influence it? These aren't questions with easy answers, but they push us to think beyond the boundaries of classical physics, and even beyond the limits of everyday experience. As strange as all this is, it's only part of the story. The delayed choice experiment shows us that the observer's role is central, but it raises yet another question. What happens if we not only change reality retroactively, but completely erase the observation itself? Could we undo what's already been done? Believe it or not, quantum mechanics suggests that even this might be possible. Can you unsee something once it's been observed? In everyday life, the answer seems obvious. It's impossible. Once you've seen something play out, reality doesn't rewind and undo itself simply because you'd prefer not to know. But if the strange world of quantum mechanics has taught us anything, it's that impossible doesn't quite apply the way we think it does. This brings us to one of the most mind-bending variations of the double-slit experiment, the quantum eraser. It turns out, in the quantum realm, information about an event can not only be erased, but reality itself can seemingly adjust as if the observation never occurred at all. The quantum eraser experiment starts out much like the double-slit experiment. You have a particle, perhaps a photon, traveling toward the slits, with a screen behind to detect the results. If you don't observe which slit the particle passes through, the familiar wave-like interference pattern appears, as though the particle traveled through both slits at once. When you introduce a detector to determine the particle's path, the interference pattern collapses, replaced by two clear lines that indicate the particle acted like, well, a particle. So far, this is just wave-particle duality behaving as expected. What changes everything is the introduction of a clever trick, the eraser. In this variation, scientists allow the detector to record which slit the particle passed through, but then they create a system to erase that which path information before analyzing the results. Incredibly, When this erased state is examined, the interference pattern comes back, as though the particle's path had never been observed in the first place. It's as if the universe says, "Oh, wait, you don't really know which slit passed through. In that case, I'll act like nothing ever happened." By removing the information about the particle's path, the system reverts to a state of superposition, where the particle exists as a wave of overlapping probabilities. It's as if the universe rewinds itself, undoing the effect of the observation entirely. Now let's make this strange idea more concrete. Imagine you're holding a coin in your hand. You flip it, and someone records on a piece of paper whether it lands heads or tails. Then, just before you look at the paper, they shred it into tiny pieces. Without that record, you no longer know how the coin landed. It's as if the flip never had a definite outcome. In the quantum eraser experiment, this shredding of the information doesn't just erase your knowledge, it seems to retroactively change the behavior of the particle that had already passed through the slits. The very availability of information determines how the system behaves, even after the event itself has taken place. This raises an unsettling question. If reality can be rewritten by erasing information, what does that say about what's real to begin with? We're taught to think of the universe as concrete and objective, where events unfold in a fixed, unchanging sequence. But the quantum eraser suggests the opposite. Reality at the quantum level isn't fixed, is malleable, shaped by the presence or absence of information. If something as fundamental as a particle's behavior depends on whether we know it, then reality might not be as independent from us as we like to believe. In fact, this highlights one of the most fascinating aspects of quantum mechanics. It's not the act of observation itself that determines how the particle behaves, but rather the availability of information. When the detector records which slit the particle passes through, that information collapses the wave function, locking the particle into a definite state. When that information is erased, the wave function is restored, allowing the interference pattern to re-emerge. The quantum eraser experiment emphasizes that what truly drives the behavior of particles is the information about the system. It's not about someone physically watching or measuring. It's about whether the path information exists at all. This challenges more than just our understanding of particles. It shakes the foundations of some of the most basic concepts in physics: time and causality. In one variation of the quantum eraser experiment, called the delayed choice quantum eraser, the choice to erase or retain the which path information is made after the particle has already passed through the slits. And yet, the interference pattern or lack of it adjusts accordingly. It's as if the particle's past behavior is rewired by a decision made in the future. This turns our everyday understanding of cause and effect completely upside down, suggesting that time in the quantum realm isn't linear. Could it be that reality at its most fundamental level is less about matter and more about information? If particles can oscillate between wave and particle states based merely on whether we can know their history, it suggests that information is the key to shaping the physical world. Some physicists argue that this aligns with the idea that observation itself is not passive but active, playing a fundamental role in defining the systems we observe. But here's where things take another leap. If the absence of information restores a state of superposition, does this mean reality is something that operates more like potential energy than solid fact? And if so, who or what decides the outcomes? The quantum eraser experiment doesn't only push us to rethink the fabric of reality itself, it also hints at the possibility that consciousness, or the role of observers, is deeply entangled with how reality plays out. We started with the question of whether you can unsee something, and quantum mechanics answers with a paradoxical yes. But instead of providing clarity, this experiment opens an even deeper mystery. If reality can indeed rewind and reassemble itself based on present or future choices about information, what does that make us? Passive spectators in a cosmic theater, or active participants shaping the story as it unfolds? How far does the observer's influence really go? These are the kinds of questions that redefine what it means to exist in a universe that's as fluid as it is strange. So here's the big question. Is reality something we observe, or is it something we create? This may seem abstract, but the experiments we've discussed lay an intriguing foundation for exploring it. From the double-slit experiment to quantum erasers, the role of observation seems inescapable. It's central to how particles behave and how reality presents itself. But does that mean the universe only forms itself when we, as conscious beings, are paying attention? Or is there something more fundamental at play here? Let's start with two opposing ideas about reality. George Berkeley, an 18th century philosopher, believed that reality is deeply tied to perception. Berkeley proposed that existence itself relies on being observed. In his words, to be is to be perceived. Under this lens, the peculiar results of quantum experiments make a kind of strange sense. If no one is watching, particles remain in their wave-like state, as though reality is on hold, waiting for an observer to activate it. But not everyone agrees with this view. Bertrand Russell, for instance, argued for the existence of an external reality, independent of our perceptions. In his perspective, our sensory data, what we see, hear, or measure, doesn't create the world but allows us to infer its properties. While we may observe reality, we're not the reason it exists. For Russell, reality is already there, but what we perceive is just a filtered version of it. Let's start with two opposing ideas about reality. George Berkeley, an 18th century philosopher, believed that reality is deeply tied to perception. Berkeley proposed that existence itself relies on being observed. In his words, to be is to be perceived. Under this lens, the peculiar results of quantum experiments make a kind of strange sense. If no one is watching, particles remain in their wave-like state, as though reality is on hold, waiting for an observer to activate it. But not everyone agrees with this view. Bertrand Russell, for instance, argued for the existence of an external reality, independent of our perceptions. In his perspective, our sensory data, what we see, hear, or measure, doesn't create the world, but allows us to infer its properties. While we may observe reality, we're not the reason it exists. For Russell, reality is already there, but what we perceive is just a filtered version of it. But how does that fit with our everyday experience? Well, consider something called the Hawthorne effect. It's a psychological concept that shows how people's behavior changes simply because they know they're being observed. In one famous example, researchers found that workers in a factory became more productive when they were aware that their performance was being watched. The actual working conditions didn't matter. They worked harder when they knew someone was paying attention. In some ways, the quantum observer effect operates on a similar principle. Observing particles doesn't just reveal their behavior, it actively changes it. This parallel between the human-level Hawthorne effect and quantum observations raises an uncomfortable question. Is the universe itself performing for us as observers, the way humans might perform under scrutiny? If that sounds a little far-fetched, consider how often the act of observation shapes outcomes in ways we don't even realize. In our daily lives, observation isn't neutral. It influences everything from how people act to how systems respond. Quantum mechanics takes this idea and magnifies it to the extreme. If particles can exist in a state of pure potential until measured, doesn't this suggest a universe that's far more dynamic and participatory than we'd ever imagined? But if that's the case, does it require consciousness to fully finalize reality, as Berkeley might argue? Or, as decoherence implies, does reality simply emerge as a byproduct of interaction, regardless of whether anyone is there to notice? And here's another layer to think about. If reality hinges on information rather than physical matter, what does that mean for the nature of existence itself? The quantum eraser suggests that even after something has been observed, removing the information about that observation can cause the system to revert to its previous state. This highlights how critical information is to how particles behave. It's less about the physical act of measuring and more about whether the information exists. So if reality is shaped by information and not necessarily by conscious observation, are our lives rooted more in a flow of data than any solid objective world? To make this idea more relatable, think about the way you might act differently if you know someone is watching you. You speak more carefully, behave a little differently, make decisions in ways you wouldn't if you were completely alone. Now extend that same idea to the universe. Could it be that the building blocks of existence adjust themselves similarly, shifting depending on the attention they're receiving or the information being extracted from them? This comparison isn't perfect, of course, but it shows how observation at every scale is far from passive. It's an active part of how things play out. So, does reality need us to exist, Or are we just participants in something larger, something that unfolds with or without us? While decoherence complicates the idea of conscious observation being the sole driver of quantum behavior, the role of the observer, whether person, machine, or environment, remains central. The key message of quantum mechanics is that observation is not passive. It shapes, defines, and maybe even creates what we perceive as reality. Whether it's through consciousness or physical interaction, the act of observing seems to rewrite the universe moment by moment, filling in the gaps of what we call existence. And if that's true, the implications are staggering. Every moment, every act of perception might be far more connected to the universe's unfolding reality than we've ever imagined, which leaves us with a larger question. If reality is defined by observation, does free will play a role in shaping it? Or are we bound by the same laws of probability that govern the quantum world? The double-slit experiment reveals something extraordinary. Reality isn't fixed, it's something shaped by observation. When particles behave as waves or particles based on whether we watch, it becomes clear that the act of observing changes the very fabric of how the universe unfolds. This idea challenges everything we think we know about causality and determinism. But here's the bigger thought. What if your role in the universe is more critical than you realize? The quantum world shows you're not just a bystander, you're a participant in creating reality itself. So next time you see the moon, ask, is it there, or is it waiting for you?